Alright, so let me adjust this just a bit. Seems to be focusing. Okay, so now we're going to start more of the practical type of thing, trends and electron configuration. Typical first year stuff. So I'm just looking at the book here. One of the popular trends is the concept of ionization energy. So what does this mean? Ionization energy is I have some atom, let's just call it atom A, and by definition, most of these is supposed to be, take one of the atoms, if we can study it, hopefully in gas phase, and technically you can put almost any one of these atoms into gas phase, and you are going to knock an electron out. So you leave it with a positive charge plus an electron. And the reality is you basically have to add some quantity of energy. So in other words, how easy is it to give this thing enough energy to, bink, knock that electron out? So let's do a quick example using electron configuration. Why don't we start with the first one? I mean, the very first atom, the simplest, it could even just be hydrogen. So if you're going to draw an electron configuration energy level diagram, you would say there is a 1s and there's one electron in it. And you know that you have the 2s, the 2p's, and this goes up. And the higher in energy you go, your textbook says the energy spacing between the orbitals get closer and closer together until you reach this sort of ceiling, if you will. So there actually is an energy difference right here that represents the limit when the electron is no longer in the atom itself. So you give that hydrogen atom in its ground state just enough energy, this much, that electron, bink, is gone. So you could take energy, nail this thing with it, and lo and behold, you get this. Okay, and the energy for that one, I don't have an actual number on it, but the trends in the periodic table graph is putting it at roughly, let's just say approximately, I'm reading it right off the graph, 1200-ish kilojoules per mole. So this is where in first year we stop and say, what does this mean? Is it one atom that takes this much? No. It's if I had 1 mole of hydrogen atoms, gas phase, I'd have to deliver that much energy so that the entire 1 mole of them is missing an electron. They're all ionized like that. So the next thing is, go to the next one. Let's go to helium. So helium, and the other thing I could have noticed is electron configuration for this is often drawn out this way, 1s1, right? So you notice that a lot of people in high school say, okay, this one would be 1s2, and it's ground state, but I want the energy level diagram. So I'm just going to say this is your energy scale, this is the 1s, here's the 2s, and on we go. Now we have a 2-electron system. Notice how for the hydrogen I drew the 2s and the 2p together degenerate, because we talked about that. Now, as soon as you have more than 1 electron, you have to have your 2p, which is coming next, different, and then your 3s up here, right? So, but it has 2 electrons, and you have to spin pair them when you're filling it in. Okay, so what they have calculated and shown is even helium has its own sort of ionization limit, where one of these electrons requires this much energy to knock it out. And it turns out when you look on the table or the graph, it jumps up to almost like 2200 kilojoules per mole. So this is the trend. In the periodic table, we went from hydrogen and we went across over to this one. Now everybody will tell you this very first row, all you have is 2 atoms. It's not quite the same as when you have a 2s and then you have the 2p, right? But the point is, one of the generic rules says that when you go from left to right, it's going to be harder to knock that first electron out. And part of the reasoning is this: the hydrogen has +1 charge, and you only have 1 electron allegedly in this density. So how much of the positive one does this see? Well, all of it. But over here, you have a +2 nucleus, much greater positive charge. And even though you have 2 electrons here, the point is, any one of these electrons, wherever and however it is, it feels more positive charge than this sense. So that's where that use of the word effective nuclear charge is used in other courses. Basically what they're saying is, how much of this charge does either one of these electrons see or feel? that's a greater effective nuclear charge that it feels, and therefore it's harder to energetically knock it out. Other people will say things like, anytime one orbital or even a full block of 3 orbitals, these ones can be either half full or completely full. This one, when it's totally full, they'll also say there's an energy sort of stability to that. So to undo that stability takes more energy to ionize it. So whether you want to talk about 2 electrons seeing more positive charge, or whether you want to say it's completely filled, you'll read it in the textbooks, they'll say things like this. These are trends, folks. These are very genetic. I don't put much faith in it other than to give them what they want to hear. It's not as good as even in university now you have software, student software that can even give you more accurate energy values, right? These are generic trends. That's what we're doing. So now we'll move on to the concept ionization energy. Now, when you go from helium to the next one, which is lithium. So now you have 1s to 2s1. Energy level diagram. Bing, 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 bing. That's 1s, that's 2s, you're like that. And your energy limit, right? So this is, now you have a 2s electron that in your energy level is higher than the 1s. So already it is closer to the energy required to take that 2s1 and go bink. So it stands to reason when you drop from one row downwards, it should be easier to knock it out. So from this is a classic diagram that you'll see. This is from Zumdahl, 8th edition. It's what we use and teach with. It's just one figure I'm showing here, and you did a great job. But there's helium, and see how it drops. And then you can see the trend, and this is what I would show. So that gives you values that have been actually measured. But I think you get the gist. And what they'll say is, when you jump from the 2s block, so you move on to beryllium and you go to boron, right? So then you have beryllium, which would look like this, 1s, 2s, 2p, bing, 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 bing. And now you move on to boron. So boron would look like that. So I think you could see, if someone's going to estimate, as you go across, the generic trend is that it should become harder to knock one electron out because the number of protons in the nucleus is going up. So one of these electrons, in an average sort of way, is feeling and seeing more than beryllium, should be harder to knock out. But it turns out, at the beginning level, and you have to memorize this lithium is sitting at roughly 500 kilojoules per mole. The beryllium, which is next, is sitting at approximately 850-ish. I'm approximating these, but the trend is obvious. Now boron. Now that you go up to boron, which has one unpaired electron sitting here, they're claiming that boron has a little bit of drop. Maybe it drops to 800. So now they're going to have a question in the back of the book. Wow, explain why boron has a lower ionization energy than this, even though the general trend is when you go across it's supposed to be harder. But boron is that first little glitch where it drops compared to that one. The only way you're supposed to be able to babble about this is to look at these two energy diagrams and say something like the 2p is actually technically higher in energy, but what you cannot say, see this energy spacing is not the same as beryllium's energy spacing to its limit. Because remember how we said for many electron systems, these orbitals as we're doing it here, it's not like they have the exact same distances from one atom to another. They're a different system, and these are model approximations. So you can't trust this spacing argument. And that's why the textbook will say things like, the difference between beryllium is you have a closed full orbital that quantum mechanical calculations clearly show there's a better energy stabilization for this than there is a lone isolated unpaired electron, not even half-filled p block. There's no energy savings for this. So this one technically, so long story short, what I'm telling you is You almost have to memorize some of these little glitches, and you have to give them the answer that textbooks normally talk about, how they verbalize it. How real is this? When you get into university and grad school and they have student software that calculates the exact number for you or very close to it, like, you really don't need these hand-waving arguments. There's a generic trend. We already know that doesn't hold. And the next question is this half-filled versus fully filled thing. So somebody could say, oh, why going from carbon to nitrogen, nitrogen to oxygen, why is it easier to knock that out? Well, nitrogen to oxygen, 1s, 2s, 2p. So you write this out, and what you'll find is, and I'll show you, you have the 1s blocks, pretend these are empty, or 1s gets filled on your way to nitrogen, right? The 2s is filled, and then you go 1, 2, 3 in the 2p. So here's the 2p. We said 1, 2, 3. Whenever you're filling them in degenerate orbitals, you're supposed to fill in each electron independently first before you start pairing them. So now you go to oxygen, right? Oxygen has one more electron in the 2p block than does nitrogen. So take a wild guess what they're going to say here. Why is oxygen a little bit, and we're going to put this one at 1250 kilojoules per mole to knock one of those electrons out, versus this nitrogen, it looks like you're looking at like 1400-ish, close, estimated numbers. Actual values exist in some damn table in there. I just didn't bother. I'm looking at the graph, and I'm estimating. So the question is, why? And you know what you're going to say? You're going to say, well, nitrogen has this special, because textbooks told me so, their special half-filled block, such as this one, has extra energy of stability, which means it's harder to knock one of these out and break the half-filled configuration, versus this one, oh, you get this stability of being half-filled when this oxygen loses this one. That's why it's a little less energy than this one to give up one electron, so that if you minus one electron, guess what? And there's the key word. If this is oxygen plus one, because you knocked one of those electrons out, now oxygen becomes isoelectronic, which means the energy level diagram with arrows for electrons looks identical to the nitrogen. But the difference, of course, is oxygen has the plus one. So it's isoelectronic with this, half-filled stability. Therefore, it's easier to knock out this electron than one of these in nitrogen. That's the answer that you would write, stuff like that. So it's left up to you to look at, you're always going to have these types of diagrams to make these arguments that you'll read in the textbook for trends in the periodic table, ionization energy questions. So we'll stop there for ionization energy, and we'll come back and we'll just move on to the next type of trends, and we'll try and finish that out. But this is demonstrating, sort of for the first time, these types of analyses in the energy level diagram with the electron configuration shown, the things to say and how to write it. That's the best way to answer them.